the difference between an egg and an elephant? What's the difference between a short loop and not sizing pipe for efficiency? Anybody in the geothermal industry knows not to short a loop. You've got to have adequate loop to keep the temperatures in that range that we have deemed acceptable in the industry, roughly 30 to 95 degrees. If you can stay within that, you're doing okay. But if you can't answer this question, then in addition to not shopping for eggs, I would not want you to design my geothermal system. Because frankly, there is no difference between a short loop and not sizing pipe for efficiency. Customers are paying way too much money for a geothermal system to end up with undersized pipes because that's the way we do it. They both cheat your customer. CV, it's a term we often see on valve spec sheets. It's quite an interesting concept. And now I'm going to ask you guys, can you tell me what a CV is? What is our level of competence? Often referred to as a pressure drop coefficient. And knowing what it means and how to use it is very important in the design process. So I'm glad we've got an honest group of folks out there, because quite honestly, when I talk to folks, they don't really know what it is. So let me find my mouse again to click somewhere. There we are. It is the flow rate in gallons per minute at which the pressure drop equals 1 psi. It's very handy because if you know the CV rating, you also know that it correlates to 1 psi. And from those two data points, you can calculate a pressure drop rather easily. So in this graph, I've illustrated this 100% to be the CV. You may have a valve with a CV of 20. So that means at 20 GPM, you've got a pressure drop of 1 psi. And if we double the flow rate, indeed, our pressure drop goes up by a factor of 4. It's going to obey that squared relationship. And if we reduce the flow rate to perhaps half, 0.5 squared is 0.25, which now gets our pressure drop down to 0.25 psi. So starting with this value right here, which is your CV rating, down here, could be 10, could be 20, could be 200. But starting from that point, you can reduce the flow rate through that device, and the pressure drop will drop according to this parabolic relationship. And I'm suggesting that we want to design systems so that every element of the system, and CVs are not applied only to valves. They are also applied, you can calculate a CV for everything. A heat pump could be expressed as a CV, pipe, lengths of pipe. So my point is, stay on top of those CV numbers for elements in your system and try to pick a size that allows you to stay down in this regime. Now, how do you size your pipes? It's a question I ask all the contractors that I deal with. Well, how are you picking that size? It could be by experience. I simply know what size to use. And I'll tell you, there's a lot of guys out there that'll tell you that. Inventory. Oh boy, that all too often becomes the selection means. What do I have in the truck? What do I have in the shop? What can I get right away? So we end up picking pipe sizes that may end up penalizing a system. How about flow capacity? Sort of like experience. Everybody believes that a certain pipe can handle so much flow, and it's strictly based on diameter. 7 feet per second is one of those boundaries that we often define not to exceed that high a velocity. 4 feet per 100, one of the most common design practices in the engineering community. And of course, the engineer. And we all believe what he tells us. So indeed, it's all over the place. And what I'm going to suggest to you is that none of these are right. You really have to look at the application, the length of pipe. You cannot afford to run 1,000 feet in a pipe that gives you a pressure drop of 4 feet per 100. That's 40 feet of head loss just because you got to go a long ways. Geothermal deserves better. Because not all pipe materials are the same. High density polyethylene DR11 is pretty much the norm in our industry. And with the introduction of PE 4710 or the ISO standard PE 100, these are the stronger resins, and we're seeing a movement towards a little thinner wall as a result. We can do copper piping inside the building. Certainly outside the building, only HDPE. Inside the building, we have a lot of choices. And the question is, how do these affect the performance of the system? You notice I didn't even put steel on here because frankly, I don't like to see steel pipe in a geothermal system. But anyway, here's a table illustrating the inside diameters of the various pipe materials for the smaller pipe sizes. Now granted, as you get into the bigger pipe sizes, you won't see the big variation in diameters as much, but this sort of illustrates my point. And I, for one, can't determine a whole lot from a bunch of numbers just by looking at it. So let me do this. If it's smaller than DR11 HDPE, I put the red background. If it's bigger, I'll put the green background. So we've got like PEX tubing over here that is a good 20% smaller inside diameter for the same nominal size. A lot of guys use PVC, and it makes them feel better to use Schedule 80 because it's stronger. It'll hold up better. But they're paying a big price because Schedule 80 will have a much smaller inside diameter. What happens to the CV of a given length of pipe? Our CVs for Schedule 80 PVC are a good 20-30% lower, so they can accommodate 20% less flow and have the same pressure drop as DR11 polyethylene. What's interesting, and you can see the simple move to go to 13.5 diameter ratio, we open up 10%, 9% more flow capacity at the same pressure drop. And there's fundamentally less material in the pipe. Now, it won't necessarily cost less because the pipe manufacturers have figured out that using the stronger resin deserves a little higher price, but indeed it is less material, more sustainable. Looking at pressure drop impact, basically inverting the CV, and we can see the pressure drops could be 15, 20, 30%, even 200% higher for different materials. So you can't simply pick a nominal size and say it's good for a certain flow rate. Pipe sizing for geothermal. Don't cheat your customer. Be generous with pipe size. Yes, it's going to cost him more money. But guess what? The entire geothermal system is going to cost him more money. And he's not buying the word geothermal. He's buying performance. Design for efficiency. Critically important. Geothermal deserves this. The interest in geothermal pertains to performance. Therefore, sizing pipes is critical, and based on length and material, a diameter can be selected to maximize pumping efficiency, and it all comes back to the pump horsepower required to achieve the flows we need. I actually did an energy audit on a geothermal system in Pennsylvania. It ended up costing more to operate the circulating pumps than it did all the heat pumps combined. To call that system geothermal is inappropriate. So how important is this? Let's do a little quiz here. For a typical 3-ton water-to-air application in a house, how much could the seasonal COP improve? By simply designing the piping so that a single 2699 Grundfos circulator could be used instead of 2. And our industry always identifies as 3-ton being in that gray area, that sometimes we need 2 pumps, sometimes 1 pump will work. So if some of you could weigh in, we'd appreciate it. How important is this issue? And indeed, I think we've got a lot of folks out there with some insight that indeed sizing the pipe and lowering pumping energy can be very significant. Excellent. I'd like to see that. That mouse go again. There we go. And the answer is, let's take the average COP of the heat pump only, and this is real data, that at a 3.75 COP under full capacity, 4.33 under part load, here's your average capacity. Annual run hours per year, you might get 700 hours a year on full load, 1,800 on part load for a total of 2,500 hours a year in operation. The BTUs delivered, we do the math, 700 times 30,000, we get roughly 21 million on full capacity, nearly 43 million BTUs on part load, for a total of 64 million BTUs. And that's pretty typical. It's roughly 20 million BTUs a year per ton in a normal application, in heating in the northern climates. You can look at the kilowatt hours based on capacity and COP. Here's the kilowatt hours, and we add those up. So for a season, the heat pump by itself will have a COP of 4.12, dividing total BTUs by total kilowatt hours gives us the COP. Now, the kilowatt hours for 2 pumps at 440 watts per pump turns out to be 1,100 kilowatt hours a year. And we have to add that to the system. We recalculate our COP, and indeed the 2 pumps will drop the COP from 4.12 down to 3.32. If we could get away with 1 pump at 220 watts, it's only a 550 kilowatt hours. Our new total, our COP is now 3.7. So we can, with a net increase of over 10%, by simply maybe going to 1.25 inches instead of 1 inch here or there, or looking at the loop field design instead of 1,000 feet of 3/4 inch, we bring it back to 800 or 600. We could even do 500, but maybe add another circuit. So we'd have 4 circuits instead of 3. There are design choices. I have a contractor in Buffalo, New York, who designs and gets away with 1 pump on 5-ton systems. Moving on to the third act. I call it the Great Hydronic Heist. And I do like this painting. So, question, do you design or install hydronic systems using water-to-water heat pumps? Certainly hydronics up in Wisconsin, Minnesota is very popular. In the